Finding roots. Square root. The square root of b, denoted with this symbol over the number b, means the non-negative real number whose square is b. So, the square root of 25 is equal to 5 because 5 squared is equal to 25. So we're looking for the non-negative real number whose square is b, the number underneath. So we're thinking, what number do I have to square to get out 25? So what it really comes down to is knowing your perfect squares. So that's why they're listed over here to the right. These are the values that you would have to have memorized. These perfect squares equal the values to the right. So you're going to be given the values on the right and asked for what number squared gives you that value on the right. Now, notice that it says non-negative real number whose square is b. And that's because, if you think about it, if I take negative 5 and square it, I also get 25, because remember, this is negative 5 times negative 5, which is equal to a positive number. So by definition, I ignore that. So by definition, we're going to choose the positive value. So the square root of 25 is positive 5 because 5 squared is 25. Let's talk a little bit about notation. So this symbol here is called the radical sign. The number under it is called the radicand. So the number that goes underneath it is the radicand. And together, it's a radical expression. Now here are a couple of warnings. I cannot have a negative number underneath the radical sign. I cannot have a negative radicand. That does not equal a real number. It doesn't make sense to square a number and get out a negative. And another warning is that if I have the radical sign with a sum underneath it, I cannot split that up. Or even if it's a difference, I cannot split that up into two separate radicals. In this example, let's go ahead and evaluate each of the following. In part A, we have the square root of 81. So what number do I have to square to get out 81? That is the number 9. The square root of 81 is 9. So what's going on is the reason this works is because 9 squared is equal to 81. We don't have to write this work, but this is why the square root of 81 is 9, because 9 squared equals 81. In part B, this is a radical expression, so we have two different square roots added together, so we'll evaluate each one separately. The square root of 64, we're looking for what number squared equals 64. So this first part is positive 8 plus the second part, the square root of 36. What number squared equals 36? That would be 6. And now we simply add each one together. So we get 14. And now moving on to part C, I have the square root of the sum 64 plus 36. If you look at part B and part C, these are two different radical expressions. This is two different terms added together. This is the square root with a sum as the radicand. Now, the square root is a grouping symbol, so we're essentially following the order of operations. We have to work inside the grouping symbol first. So we have to add 64 and 36 together as our first step, which is positive 100. And now the square root of 100. So what number squared equals 100? That's going to be positive 10. And now we move on to part D. We have negative on the outside and the square root of 9. Since the negative's on the outside, it stays on the outside. It's like a negative 1 times whatever the value of the square root of 9 is. So the value that we have to square to get out 9 is 3. So it's like negative 1 times 3, which is -3. It's very important that the negative was on the outside. In part E, the square root of -9 is non-real. So this is a non-real answer. So we cannot find a solution to it. There is no number squared that gets me to a -9. Because remember, when I square something, it makes it positive. So this doesn't make any sense. This is a non-real answer. In this example, we want to approximate the square root of 19 on a number line. Here we have a radicand that isn't a perfect square. There's no integer that we can think of that we multiply to itself or square to get out 19. So we're stuck approximating this value. So to get started, let's think about what is the largest perfect square that is less than 19. So let's remember our list of perfect squares. We have 1, 4, 9, 16, 25, 36, and I'll just put ... So the largest perfect square that's less than 19. So 19 fits right here in between 16 and 25. So the largest perfect square less than 19 would be 16. And then what is the smallest perfect square that is greater than 19? So what's just above it, but that's still the smallest? So that would be 25. So essentially trying to figure out where does 19 fit in that list of perfect squares. Well, it falls between 16 and 25. Now, how does that help us? Well, the square root of 16 is a value we can find, and the square root of 25 is a value we can find. So I'm going to go ahead and draw my number line, and I'm going to go ahead and label the square root of 16 and the square root of 25. Because those are nice values, the square root of 16 is 4, and the square root of 25 is 5. And so now I want to think about where the square root of 19 falls here. So let's go ahead and think about the halfway point. So that would be 4.5. And if I think about these radicands, 16 and 25, the value that's halfway between 16 and 25 is 20.5. So in the middle is about, so I'm just going to say approximately, the square root of 20.5. So we're looking at halfway between 16 and 25. So that means that the square root of 19 is going to be a little bit less than that. So we can go ahead and sort of approximate the value right here is where it would go. Somewhere between 4 and 4.5 is the square root of 19. Now, in that last example, we had a radicand that was positive and not a perfect square. So what happened was the square root was actually an irrational number. The square root of such a number, it is a real number, but it is non-repeating and non-terminating as a decimal. So it just keeps going on and on forever, and it doesn't repeat or have any pattern to it. And one of the ways to evaluate this type of square root is to approximate it using our calculator. So we did the last example, just doing a rough approximation with our understanding of square roots, but we can also use our individual calculators to approximate these values. So approximating the square root of 21 using a calculator, we get 4.58257. So I'll just go ahead and stop there at 5 places past the decimal, but know that it does keep going on and on and on, because this is going to be a non-repeating, non-terminal, as in it doesn't stop, decimal. So that's why we have to approximate the value. Now let's move on to cube roots. The cube root of b, with this notation here, where this time the radical symbol has a 3 in the upper left-hand corner, means the number whose cube is b, the radicand. So the cube root of 8 is 2, and that's because 2 to the third power, 2 cubed, is equal to 8. So what this comes down to is knowing your perfect cubes. So here are the perfect cubes that you should be familiar with. And we're actually going to have to recognize the right-hand side, that with looking at a number, like let's say 125, that is 5 cubed. So these are the ones that we need to be familiar with. Let's take a look at an example. Evaluate the cube root of 64. So we're thinking, what number to the third power equals 64? So if I reference over here, I have 4 cubed equals 64. So that means 4 is the answer. Now, this next one is the cube root of negative 27. And some students might put that this is a non-real answer. But in a cube root, I can actually have a negative as the radicand and still get out an answer. That answer will just be negative itself. So the answer here, I'm still thinking about the fact that 27 is 3 cubed, but my answer is going to have to be negative 3. And I'll put y below because negative 3 in parentheses, that is so important, negative 3 in parentheses cubed is negative 27. Because remember, negative 3 cubed is negative 3 times negative 3 times negative 3. And so when we multiply the first two, we do get a positive 9, but then times another negative 3, we get a negative 27. So the cube root, right, the base here, was a negative 3 that got us to that radicand of negative 27. In this example, we're going to generalize what we have been doing with square roots and cube roots. The nth root of b, denoted with a little n in the upper left-hand corner of the radical symbol, means the real number to the nth power is equal to b. Now, if n is even, if we're taking an even root, the root must be non-negative, so our answer must be non-negative. An even root of a negative number is not a real number. So if we have a negative under here and we're taking an even root, then the answer is not a real number. It's non-real. So here, this nth root, when there's no number written here, we assume it's square root. That's what we were doing in the first place. So if I have this symbol here, this is a square root. We don't write a 2 here, but it's implied that it's a 2 there. So 2 squared is equal to 4. We don't ever write it though, only if it's something higher than 2. So we could have a bigger number here, like a cube root, or higher is when we would write it. So let's take a look at some examples with different roots. So we have the fourth root of negative 16. We have an even root. We have an even root because 4 is an even number. When that happens, we're not allowed to have negatives underneath. We can't have a negative radicand because then this is a non-real number. This is a non-real number. So we move on and we look at the next example, the fifth root of negative 32. So we can have a negative as the radicand because 5 is an odd root. So in an odd root, like the cube root with the 3 here that we looked at earlier, we were allowed to have a negative underneath. But now it's a matter of, we're thinking, what number raised to the 5th power gives me 32? So we have a list of a couple of powers here that are higher. So we have to the 4th power and to the 5th power. Well, 2 to the 5th power is equal to positive 32. So since I want a negative 32, I'm going to have to use negative 2. So I'll write y below because negative 2 to the 5th power, the negative 2 in parentheses, is equal to negative 32. Is equal to negative 32. So there's not many, but there are a few of these higher exponents that we do need to be familiar with and recognize when dealing with these higher nth roots. One of the places square roots appears is in using the Pythagorean theorem, which we looked at previously. A squared plus b squared equals c squared. In this example, two sides of a right triangle are a equals 2 and b equals 3. Use the Pythagorean theorem to find the length of the hypotenuse. Let's go ahead and substitute a equals 2 and b equals 3 into our equation. So we start with a squared plus b squared equals c squared. So we end up with 2 squared plus 3 squared equals c squared. Well, this is 4 plus 9 equals c squared, or 13 equals c squared. So now we end up with the fact that c squared equals 13. So that must mean that the value of c is the square root of 13. So c is equal to the square root of 13, because we're talking about a right triangle, so the side lengths have to be positive. So we're sticking with a positive square root of 13. So we could typically plug in a negative and square it and get out a positive value, but we want our side lengths, so we have a equals 2 and b equals 3, but our side length, since we're talking about an actual triangle, has to be a positive number. So we're going to stick with the positive or non-negative square root. So we have c equals the square root of 13.